Hi guys, welcome to the second lecture in our equilibrium unit. This lecture is going to focus on why the equilibrium constant is important and what it can tell us about the reaction and really what it means. So this is kind of looking at the definitions and everything that we talked about in the first video, but giving it more of a meaning. And this is based on sections 15.3 to 15.5 in your book, so I'd highly recommend that you take a look at those sections. So just to review, KEQ, which is the equilibrium constant, can be expressed in two ways. We can talk about Kc or Kp. Kc is based on concentration. So if we want the concentration, so if the problem asks for concentration, we're going to use Kc, and we're going to do that by using the brackets that represent concentrations. So it's always products over reactants. If it's Kc, it's going to be concentration of products over concentration of reactants. Now, this is even if the reaction includes gases. If it's Kc, you always include concentrations. Then we have Kp. Kp, remember, is based on pressure. If the problem asks for Kp, then we're going to represent it like this. Again, products over reactants, but now rather than having concentration, we have P to represent the partial pressures. With Kp, you can only talk about gases because aqueous solutions don't have a pressure. So remember also when we want to write the equilibrium constant expression, it's only for aqueous or gases. All right, so only aqueous or gases. And then remember that the equilibrium constant is a ratio of not only concentrations or pressures of products to reactants, but it's also a ratio of forward to reverse rate constants. Because at the beginning of the first video, we looked at how the kinetic definition of equilibrium kind of derives the equilibrium constant, and that's because the forward rate constant over the reverse rate constant is equal to some constant, which is actually KEQ. So now looking at 15.3, this is looking at the magnitude, so the value of the equilibrium constant and what it means. So the equilibrium constant, which is KEQ, again is the ratio of products to reactants. So products are always on top, reactants are always on the bottom. The larger the KEQ, the more products you have present. Because if you have a large KEQ and you have products over reactants, think about what that means. If KEQ is large, that means that your product concentration is also large. So products are present, more products are present at equilibrium. And we know that in terms of having a larger K, that means KEQ is greater than 1. This is considered a favorable reaction. What that means is the reaction will most likely proceed because we'll have more products than reactants at equilibrium. So we could think that the forward reaction, the forward reaction is going to be the one that is going to be more likely to occur. The smaller the KEQ, which means that it's less than 1, so the smaller the KEQ, this is unfavorable because what it means if KEQ is smaller is that your reactant concentration is larger. So if you have a small KEQ, that means that you have more reactants at equilibrium, which means the reaction doesn't really proceed very much if we have more reactants than products. So this is unfavorable. So the more products you have, the more favorable the reaction. The more reactants, the more unfavorable it is. Okay? And the larger the K, the more products you have. Now, if KEQ is much, much greater than 1, then products dominate at equilibrium. What that means is you're going to have significantly more products than reactants. And what we say is equilibrium lies to the right, which means the forward reaction is going to be the one that is going to be more likely to occur. Now, if KEQ is much less than 1, that means that you have significantly more reactants at equilibrium, which means equilibrium lies to the left. And what that means is more than likely the reverse reaction is going to be the one that's going to occur more than the forward. So this just gives you some visuals to look at how to represent K and really what it means. So if we take a look up here at the top, okay, so up here at the top, here's where Kc or Kp equals 1. That means that you have an equal amount of reactants and products at equilibrium. Now, if we have a very large K, that means the reaction proceeds to completion, right? Very large K means that you have more products. Now, if K is very small, that means the reaction proceeds hardly at all because we have more reactants. So then this second graphic just gives you another idea. If K is much greater than 1, it lies to the right. Notice the forward reaction is going to be the one that's going to happen more. And then if it's significantly less than 1, the reverse reaction is going to be the one that's more likely to occur. Okay, so when we look at the direction of the reaction, so whether we look at forward or reverse, and K, so we're going to look at the direction of the reaction and the effect that it has on the equilibrium constant. So as I talked about in the first video, equilibrium can be approached from any direction, right? You can either approach it going from the forward reaction, or you can approach it going from the reverse. Now let's consider this reaction. This is the one that we talked about in the first video. So we have N2O4, and that's a reversible reaction. We know it's reversible because we have this double arrow right here. And then that produces NO2. So the equilibrium constant at 100 degrees Celsius, now I want you to think about why is this important? Well, it's important because rate constant is temperature dependent, which means the equilibrium constant is temperature dependent. So equilibrium constant we have is K equals, and this is going to be Kp because we have gases. So if you're not told which K it is, use the equilibrium constant expression that makes the most sense. If you have mostly aqueous solutions, use Kc. If you have mostly gases, use Kp. So we have the pressure of NO2, and that is squared, products over reactants, which is the pressure of N2O4. Okay, so here's our Kp. Now when we write the equilibrium expression for the reverse reaction, right, again, it's at 100 degrees Celsius. We get Kp equals the pressure of N2O4 over the pressure of NO2 squared. And I want you to take a look at these two. Okay, what do you notice? What do you notice about these two? Well, they're the reciprocal. So the equilibrium constant for reaction one direction is the reciprocal of the equilibrium constant in the opposite. And this gives just a general way to look at it. Notice that you have K for the forward. If you flip it, it becomes 1 over K. Now, the equilibrium constant of a reaction that's been multiplied by a number. Okay, so let's say that we have A plus B yields 2C. That gives us K, right? That equilibrium constant is K. Well, if we multiply it, we don't just multiply K to become 2K. Okay, because when a reaction is doubled, what that means is we are now taking, in this case, let's say we have the concentration of C squared on the top over A times B, right? So this is simply K. Well, when we multiply the actual reaction by 2, what we do is we now have C to the 4th over A squared times B squared. So notice that we aren't simply multiplying them by 2. We're actually changing the exponents. So what happens is, instead of just having K, we have K squared now. So if you're multiplying it by 2, the equilibrium constant is then raised by a power of 2. If we multiply it by 3, then K becomes K cubed. And then the equilibrium constant for a net reaction that's made up of 2 or more steps is simply the product of those. So if we have A plus B yields 2C, that's K1. But then we have to add that to C plus A yields D. That's K2. If we want to add those together, we don't simply add the K's, we have to multiply them, because all of the equilibrium constant expressions are based on multiplication and exponents. So instead of adding these, we actually have to multiply them. So this just summarizes the tips and the tricks and the shortcuts with KEQ. These are just the three shortcuts that I just showed you on the last two slides. So then when we look at equilibrium constants, we have to look at what kind of equilibria we have. So we have the first type, which is homogeneous equilibria. And this is simply when all of the reactants and products are in the same phase. So they're all gases or they're all aqueous. Heterogeneous equilibria, which also happens quite often, is the equilibria in which one or more reactants or products are present in a different phase. So maybe we have a solid plus an aqueous solution yields a liquid plus an aqueous solution. That's a heterogeneous equilibria. Now, the value used for the concentration of a pure substance is always 1. So this is simply a reference concentration. This is why we ignore solids and liquids in the equilibrium expression, because solids aren't dissolved in anything, okay? So it doesn't have a concentration. Same with liquids. They're pure substances. Solids don't have concentrations. Liquids don't have concentrations. The only thing that we focus on are gases because they have pressures, and pressure is proportional to concentration, and aqueous because aqueous solutions have concentrations. Okay, so with heterogeneous equilibria, this is just going over what I just talked about with solids. If we talk about the decomposition of calcium carbonate, notice we have solid, solid, and gas. So experimentally, the amount of CO2 doesn't depend on calcium carbonate or calcium oxide. Well, the reason that it doesn't depend on the amounts is because they're both solids. So when we add a solid to something, that's not affecting concentration, and it's not affecting pressure. In order to affect concentration, we'd have to add a solid to an aqueous solution. Now, the concentration of a pure solid or pure liquid equals its density divided by its molar mass. So here's density, here's molar mass. Now, when we look at equilibrium, density or molar mass, neither one of those are variables. So that means that concentrations are constant. That's why they're not included in the equilibrium expression. Now, what I mean by that is, even though the concentrations of solids and liquids aren't included in equilibrium, you still need them in order for the reaction to occur. So even though we don't include it in KEQ or KC or KP, we still need them to participate in the reaction, and they have to be there in order for equilibrium to be established. If they're not there, the reaction's not going to take place. We simply don't worry about it when it comes to writing KEQ. Okay, so we looked at how to write KEQ, why KEQ is important, looking at value, so greater than 1, less than 1. Now we're going to look at how to actually calculate it based on concentrations that you're given. So when we calculate equilibrium constants, first you want to make sure that you have a balanced equation. Then what we have to do is we have to look at initial and equilibrium concentrations for everything in the mixture. If initial and equilibrium is given, we can actually calculate the change. We also want to use the coefficients, though, to calculate the changes in all concentrations. And then what we're going to do is we're going to have to somehow figure out equilibrium concentrations, and then we can calculate the value of the equilibrium constant. Now, it seems like there's a lot of steps for this, but it's actually going to be it can be summarized in 3 steps. Write a balanced equation, include your states of matter, because that's important. Write and complete what's called an ICE table. We're going to look at how to write an ICE table, keeping in mind coefficients, and then write your KEQ expression and solve for KEQ. So what we're going to do is we're going to just look at an example, and we're going to look at how to write the equilibrium constant expression and how to solve. So in this example, we have a closed system. Remember, closed system is important because we don't want any reactants or products to leave. Initially, it contains 1 times 10 to the negative third molar of H2 and 2 times 10 to the negative third molar of I2. At 448 degrees Celsius, and it's allowed to reach equilibrium. And then it tells us that analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative third. So at equilibrium, we know how much HI we have. And then it says calculate Kc for the reaction taking place. So we have a lot of information. And what we're actually going to do is we're going to put it into what is called an ICE table. So when we have this ICE table, it's for initial, change, and equilibrium. Okay, ICE, initial, change, equilibrium. It's very similar if you used a BCA table for stoichiometry. It's actually very, very similar to that. So initially, we want to plug in what the problem tells us. And the problem told us that initially we had 1 times 10 to the negative third of H2 and 2 times 10 to the negative third of I2. Notice it gave us molarity, which means which of the K's are we going to be solving for? Okay, Kc. So initially we had our reactants, we had zero product. Okay, we know that because it's a product. We're not starting with anything. And then it tells us that at equilibrium, we have 1.87 times 10 to the negative third molar of HI. Now what I want you to do is look at this and figure out, is there anything here, just by looking at this, that we can determine? Well, we can determine the change. Right? The change is simply how much is added or removed. So to get from 0 to 1.87 times 10 to the negative third, we had to add 1.87 times 10 to the negative third. Now, this is our change based on HI. Now what we have to do is figure out, based on HI, what is our change of H2 and I2? Well, stoichiometry actually tells us the concentration of H2 and I2 decreases by half of that, because if we take a look at the balanced equation, okay, the balanced equation tells us that for every 2 moles of HI, only 1 mole of H2 and 1 mole of I2 react. So what we can actually do is we can take this change of 1.87, I'm just going to put E negative 3, we can actually use a mole ratio. For every 2 HI, we only need 1 mole of H2, and in this case also only 1 mole of I2. So that's how we get these changes. Right? The changes, we have to use stoichiometry. Okay? You have to use stoichiometry for the change. Use the coefficients. And then what we can do is we can look at our initial and our change, and we can figure out equilibrium. Now, notice first that the change is negative for H2 and I2. Well, it's negative for H2 and I2 because these are reactants. Okay? It's positive for HI because it's a product. So reactants always decrease, products always increase in terms of the change. So then what we can do is we can take our initial and our change, and we're just going to simply subtract. 1 e to the negative 3 minus 9.35 e to the negative 4. We actually get our equilibrium concentrations. Notice at equilibrium, H2 and I2 aren't equal, and that's okay. They don't have to be. What we have to do, though, is we have to use stoichiometry. Now we have our equilibrium concentrations. We have our concentration of H2, we have our concentration of I2, and we have our concentration of HI at equilibrium. Okay? This is going to be important now because equilibrium concentrations are what we use to calculate Kc. So therefore, equilibrium constant, we can write our Kc expression using the balanced equation. So when we do that, we take products over reactants, and we have to take into account the stoichiometry, so it's HI squared. So what we do is we simply plug in all of our equilibrium concentrations. We multiply, we divide, and in this case, we get Kc equal to 51. Now, what does that mean? Well, Kc is much greater than 1. So because Kc is much greater than 1, our forward reaction is the one that's most likely going to occur. So this helps because this tells chemists which reaction should we expect. Should we expect the forward? Should we expect the reverse? Okay, so that is actually it for this lecture looking at equilibrium constants. And what we can do now is we're now going to do some practice with plugging everything into ice tables, solving for the equilibrium constant, and using that to determine what it means about the reaction mixture or the reaction at equilibrium.